Hi ladies, this is Mrs. Blaufuss. This is Algebra 2 with Trig in Chapter 7, and in this chapter we're looking at exponential functions and logarithmic functions. So this first chapter, or this first lesson, is about exponential growth functions. So we have a few key vocab terms. The first is an exponential function, and an exponential function, we've defined this before, but it's a function in the form y equals a times b to the x power. And a stipulation is that a does not equal 0, and that b is a positive number that is not equal to 1. The next term is exponential growth function. So this is going to be an exponential function, so it's still going to be in the form y equals a times b to the x. And the difference here is that a is going to be greater than 0 and b is going to be greater than 1. The growth factor is part of our exponential function, and that's what the b term stands for. And then lastly, the asymptote. And the asymptote is the name for a line that the graph approaches more and more closely, but it never actually reaches that line. So let's look at this key concept that's in your note sheets. And the key concept describes asymptote. And in this case, the parent function, where a is 1. So the parent function f of x equals b to the x power. That's like 1 times b to the x power. So b is going to be greater than 1. That's the parent function of the family of exponential growth functions with base b. Here you can see the general shape of this graph where f of x equals b to the x. And the asymptote for this is the x-axis. So as you can see, it gets closer and closer to the x-axis here, but it never actually is going to reach the x-axis. And then on the other side, we're in the first quadrant here, the graph rises from left to right. It passes through the point 0, 1, and then 1, when x is 1, your y value is whatever your b is. So the domain of this function is all real numbers, and the range is y is greater than 0, not greater than or equal to, but just strictly greater than, because again, since the x-axis is an asymptote, it's never going to actually reach that line. All right, let's look at a couple examples. So there's a few steps that you're going to follow when you're graphing these exponential growth functions. So we're going to graph the function y equals a times b to the x for a value where b is greater than 1. So we're going to graph y equals, here's our a value, 1/4. And our b value is 6. So when we do this, we're going to follow a couple steps. So the first step is to plot the point where x equals 0. Then we're going to plot a point where x equals 1. And then we're going to go from left to right and draw a curve that begins just above the x-axis. Because again, we know that our domain is all real numbers, but our range is y is greater than 0. And that we saw in our last slide right here, the range y is greater than 0. So we can make a little table, x and y values. So we're going to plot 0 and 1. So if we look at this function and we look at when x is 0, our y is 1/4 times 6 to the 0 power. If you remember from your properties of exponents, anything to the 0 power is 1. So when x is 0, our y is 1/4. So we're going to plot that point, 0 and 1/4, about here. And then the next one we're going to look at is when y is 1, or when x is 1. So when x is 1, y is 1/4 times 6 to the first power, which is 1/4 times 6, which is 6/4, or 3/2. So when our x is 1, our y is 3/2. So now we're going to go from left to right. We're going to draw a curve that begins just above the x-axis and passes through those 2 points and moves up and to the right. So it's going to be a curve, and you want to draw it as smooth as you can, and it takes a little bit of practice. I still am working, obviously, on my curves, but it's not going to be perfect because you're just sketching it in, but you want to sketch a curve, a smooth curve that goes through those points and does not cross that x-axis. All right, let's look at the second one. The second example here is graphing an exponential growth function. But if you look at this function, y equals a times b to the x minus h power plus k. So here we have the h and our k value. So our h value is the horizontal translation, just like our last chapter. And our k value is our vertical translation. So in this example, we're going to translate horizontally. So in this example, our h value is 2, because it's x minus 2, and our k value is negative 2, because it's plus k, in this case a plus negative 2, so our k value is negative 2. So that means we move to the right 2 units, and we move down 2 units. So in a graph where you have an h and a k value, you want to start by graphing 2 times 3 to the x. Graph this function first, and then with the points that you graph, translate 2 units to the right and move 2 units down. So let's do that. So when our y is 2 times 3 to the x power, we're going to plot x and y points. We're going to plot 2 of them where x is 0 and x is 1. So when x is 0, we have 2 times 3 to the 0 power, or 2 times 1. That's going to give us a value of 2. And when x is 1, we're going to have 2 times 3 to the first power, which is 2 times 3, which is 6. So we're going to plot those 2 points, 0, 2, and 1, 6. And then we're going to go from left to right and draw a curve that goes through those points and doesn't actually ever hit our x-axis. Now, since we're doing a exponential function that has an h and a k value, we need to take those 2 points that we plotted and we need to move them to the right 2 units and down 2 units. So I'm going to take this point, I'm going to go to the right 2 units, and I'm going to go down 2 units. So here's my new point. And then I'm going to do the same for my second point. We go to the right 2 units, and I'm going to go down 2 units. So now if I look at my domain of this function, I'm going to go below the x-axis. So if I take this point right here, if I go to the right 2 units and I go down 2 units, here I am below the x-axis. So my new asymptote actually is not the x-axis, but instead it's at the y equals -2 axes instead of the y equals 0. So the domain and the range, the domain doesn't change. X can be all real numbers. But the range, my y, is now going to be greater than -2. That's my k value. So your range is going to be greater than your k value, whatever your k value is. In this case, it's -2. In the previous example, our k value was 0. It was x, our h value and our k value were both 0. So our range was y is greater than 0. But here where we have a k value that's less than 0, that's going to be the beginning of our range. So here's a couple examples you can do on your own. So pause while you work, and then you can unpause for the solution. Remember to state the domain and the range. So you want to start by graphing the function y equals 2 times 4 to the x power, and then we'll translate those points. So start with x equals 0 and x equals 1. Then you want to translate each of those points 1 unit to the left and 3 units down because your h value is -1 and your k value is -3. So -1 unit horizontally is to the left and -3 units vertically is down. And then you'll sketch your new graph, and that's the graph that I did in green. And now we want to define our domain and range. So our domain actually doesn't change. Our domain is still all real numbers, but our range does change. So now our range, instead of being y is greater than 0, it becomes y is greater than -3, because that's our k value. That's the lowest horizontal value that we're going to have for this graph. All right, this next example is about solving a multi-step problem. So in this multi-step problem, you're looking for an exponential growth function. And so in general, if we have a quantity that's increasing by a fixed percent for a time period, the quantity after t years, so after some amount of time, we're going to use the model y equals a times 1 plus r to the t power. So y is going to be our quantity. A is going to be our initial amount, so whatever you start with. And then our R is going to be our rate of increase as a decimal. And then lastly, T is going to be our time. And we're going to use time in years. So here it's asking us to write an exponential growth function giving the number n, which is the quantity of buffalo after t years. So that's our time. And we're looking for time to be 7 years. So we're going to use this model, y equals a times the quantity 1 plus r to the t power. So if our initial population was 38, that's our a value. And it's growing by 7% each year. So to write our model, it's asking us to use n instead of y, which is still our quantity. We'll say the number of buffalo is equal to the initial amount of buffalo that we started with, which was 38, times 1 plus our rate as a decimal, which is 0.07. 7% is 0.07. And we're looking for that after 7 years. So our t is 7. So if you compute this out, you're going to get n is approximately equal to 61 buffalo, and that's at 7 years. So let's plot that point just right almost at about 60, just a little bit above. And then in order to actually graph this model, we're going to need a couple more values. So we can make a table of x and y values. Okay, where x is our independent variable, that's years, and y is our buffalo, or our dependent variable. So y, the number of buffalo, depends on how many years have passed. So we can start at 0. We did 7 already. Maybe we'll do, I don't know, 3, 5. And looks like we can do 10. So when we first start, we're going to take 1.07 to the 0 power, which is going to be 1. 38 times 1 is 38. So we know that one right away. And now I'm just going to plug these other ones into my calculator. So after 3 years, we have about 46.5. After 5 years, we have about 53. And after 10 years, we have about 74.75. So then I'm going to plot these points, and I'm going to draw my curve. So again, you want your curve to be as smooth as you can and make sure that it hits all of the points that you've plotted. So then it says to graph the model and use the graph to estimate the year when the buffalo was about 53. So I'm just going to draw a line here at about where 53 would be. So it'd be pretty close to here. So it looks like at about 5 years is when I hit that mark, 53. So pretty close to about 5 years. All right, and then our last example is about compounding interest. So you may have seen this interest formula before. A equals P times 1 plus R over N to the NT power. So P is going to be the principal amount deposited, so that's what you started with. That's similar to your initial quantity in the last formula. And it's going to pay an interest rate, an annual rate, and again, you're going to express that as a decimal. And it's compounded N times per year. And the amount A is the amount of money you have after T years. So we're looking to find the balance in the account. So in this first example, our A is unknown. That's our balance. But 2,900, that's our P value. 3.5%, that's our rate, but our rate is going to be a decimal, so it's really 0.035. And 1 is our T. And then we're going to find the balance if the interest is compounded monthly. So that means 12 times per year. Or if it's compounded annually, which means 1 time per year. So with interest compounded monthly, so we'll do this one first. What's the balance after 1 year? So in our formula, our balance, A, is going to be the principal, which is 2,900, times 1 plus our rate, which is as a decimal, 0.035, and compounded monthly, that means 12 times per year. And we're going to take that to the 12 times 1 power, so to the 12th power. And we're going to compute that. And I'm going to use my calculator for that. And when I do, I get $3,003.14. Now when I do it when my interest is compounded monthly, my formula is going to change just a little bit because I'm not going to have that N, that 12 for N. So after 1 year, I'm going to have 2,900 times 1 plus 0.035 over compounded 1 time per year. And after 1 year, I'm just going to bring that to the first power because my N is 1 and my T is 1. So if I do it this way, I get approximately $3,001.50. So the more times per year your money is compounded, the more you're going to make. And here it's not a huge difference, less than $2, but still compounding monthly as opposed to annually gives you a higher return. So please pause the video and try these next two on your own, and you can unpause for the solution. So in this first example, we're going to use our formula. The quantity equals our initial amount, so 38 buffalo, times 1 plus our growth rate, which is 0.07, to the number of years as our power. So with that formula, we get about 80 buffalo after 11 years. And in our second example, our principal amount is $5,000, 3.72%. Annual interest is in decimal form 0.0372. And we're looking for the balance, or A, after 3 years if it's compounded quarterly. Quarterly means 4 times a year. There are 4 quarters in a year. So after 3 years, we would have $5,587.45. So please jot down any questions that you have, and we can go over them when I see you in class. Thanks.